Now that you know how to find the limits by looking at a graph, by looking at a table, and maybe looking at piecewise functions, we are now going to actually find limits analytically without actually looking at graphs or tables, just looking at the function. So let's look at the first one. Find the limit, and it says the limit as x goes to 2 of this. You could draw this out, and it's a parabola, and then figure out where x is going to, when x is going to 2, where is y going to? However, it is not necessary because you can ask yourself a few things. First, is the function continuous at x equals a? So whatever the x value they want you to evaluate the limit at, you ask yourself, is the function continuous at that point? If it is, then just plug in and you're done. So very easy. If no, then you have to do special tricks. Now, if it's continuous, you know what to do. No, well, so how would you know that it's a no? Is kind of the question. So either you look at this 2 and then you say, oh, if I plug it in, something bad's going to happen to this function. And now let's kind of review what bad means. You could have a discontinuous function. So whether that means you get a hole, okay, if you kind of remember, to get a hole, that means you will get a 0 over 0. That's the indeterminate form. Or you get undefined, so you have a number over 0. You can never divide by 0. So when you have something like that happen, then we would say, something is wrong. Let's kind of double check to see if there really is no limit, or it's just that I don't know what the limit is. Okay, so the first thing, again, check to see if the function is continuous at this x value. If yes, plug it in. If not, which is the, whether the function is continuous, it's not continuous, then you do special tricks. And then how do you know that the function is not continuous? Whether you just know it because you remember how the graph looks like, or you plugged it in and then you get one of these things happening. Okay, so let's look at this first example. This is a parabola. Parabola is always continuous, so this is very easy. It will be continuous at x equals 2 because the function is continuous at everywhere. Then very simply, you put 2 into x. You get 4 times 4 plus 3. That is 12 plus 3, which is 15. So then when x is going to 2 from both sides, y is going to 15. Okay, and then it's pretty intuitive. So you have 4x squared plus 3. So it's just a parabola moved up 3 with a stretch of 4. And what's going to happen is when you're going to 2 from both sides, this is 15. That's what it means. All right, very easy. Again, first you ask yourself, is the function continuous at that point? If it is, plug it in. If not, let's do special tricks. Okay. Now, okay, so this is kind of my second point. If you cannot tell whether the function is continuous or not, you should still substitute just to see if you get one of these. Because sometimes it might take you a long time to figure out whether this function is continuous or not because it's not one of the basic parent functions. It's just better kind of substitute in and kind of try your luck. If you get a number, then you're done. You didn't really have to think about whether it's continuous or not. Okay, so then there are some tricks. So here, we're going to look at some tricks of when it's not continuous. If direct substitution doesn't work, you can try these tricks. So these are kind of the basic and general limit rules. First, scalar multiple. So that means if you have a limit as x goes to some number, and you have k as a coefficient times the function, and you're like, I'm not sure how to find this limit. Well, that k is just a coefficient, so you can just take it out of the limit and then evaluate the limit first and then multiply it by k. The second one is similar. If you have a limit of two functions added together or subtracted, and you cannot really figure out what to do when the two functions are added or subtracted, then you can actually split them into two limits so that it's easier to evaluate. The third one is kind of the same idea. So kind of think of it as like they're kind of all following the algebraic rules. So if you have a limit of two functions multiplied together, you could just say it's the limit of one times the limit of the other. And quotient is the same idea. So if you have the limit as x goes to c of, let's say, f over g, then you could evaluate the limit separately. So please do remember these limit rules for future reference. And obviously, this will not work if this is 0, so this cannot be 0. Power rule, same idea. This one is, not as intuitive. If you have the limit of something like this to an nth power, and you're not sure what to do with this nth power, and you cannot evaluate, then you can actually evaluate just the limit by itself, just the limit of f by itself, and then raise it by nth power. And same thing goes with the roots. So if you happen to have an nth root of this limit, I should probably start with it being part of the function. So if you have limit as x goes to c of the nth root of this function, then you can actually take the root out and then figure out the limit first. Okay, very kind of intuitive algebraic application, but now let's look at real application. So let's look at this first question. So it says, what is the limit as x goes to -2 of this function plus 5 times this function? And the function is so that you have to look at this graph. And you can see that there are two graphs. One is blue, one is green. The green is g, the blue is f. Well, it's kind of hard to evaluate the limit when the two limits are together. So what we can do is apply the limit rules that says you can just split them out. Or maybe we'll get really lucky and that it happens to be continuous at -2. I don't know. So let's see. At -2, it's not continuous at -2 for f, but there is a limit. So we could just plug it in, or let's kind of do it the more official correct way of separating the limits. And then since this is a coefficient, I'm going to take it out of the limit now so that I'm only really evaluating the limit at those functions at those two x values. So it's kind of a clean way of looking at it. Okay, so limit as x goes to -2 of f of x. So when x is going to -2 from both sides, f is going to 1. So this is 1. Running out of space here. 5 times. And then limit as x goes to -2 of g. When x is going to -2 at g, y is going to -1. So 1 plus 5 times -1, that is -4. Okay, second one, same idea. Limit as x goes to 1 of f times g. So again, f times g may be a little hard to figure out, so we can split the limit. And then figure out the limit for each one. So as x goes to 1 for f, that is 2. When x is going to 1 for g, there is nothing. So what is 2 times does not exist? Does not exist. You can't multiply something to something that doesn't exist and get something out. So then this is does not exist. Third one. The limit as x goes to 3 of quotient. So we could, again, split this. All right, what's going on when we go to 3? When x is going to 3 on f, both are going to 0. When x is going to 3 at g, both are going to 1. So 0 over 1 is 0. All right, really quickly, go ahead and figure out the limit for each one. Remember, the first thing you should ask yourself is it continuous at that point? And if you don't know, plug it in. You're looking for a number. If you get a number, the answer is the number. If you don't get a number, meaning you get something over 0, either way, then it's a special case, and then we'll kind of talk about that later. All right, so these 4 are all very nice. They turn out to be continuous at all those points. So the answer is as following: 39, negative 1 over 11, negative 7 over 4, and 2. Now let's get into the special techniques. So we already did this in pre-calc, but you might not have remembered this. Okay, so the first one, again, when you're looking for a limit, you always ask yourself, is it continuous at that point? If you don't know, just plug it in. Okay, so we don't know, let's plug it in. So negative 3. Negative 3 squared plus negative 3 minus 6 over negative 3 plus 3. So that is 9 minus 3 minus 6 over negative 3 plus 3. We end up getting 0 over 0. Okay, 0 over 0 means that this is called the indeterminate form. That means we don't know, indeterminate. So we don't know. What does that mean? It means that there might be a limit, but we don't know at this time. We need to do something different about it so that we can get the limit. So 0 over 0 is it's kind of an indication of a whole. If you kind of remember in Algebra 2. So then what can we do to figure out the actual limit? Well, this is called the dividing out technique. So technique number 1. All right, so here is kind of another thing. So I'm going to kind of teach you a lot of little things in calculus where you have to follow these details. If you don't, you will lose points on your test and eventually the AP test. So first thing is when you write a limit like this, until you substitute in the actual number into the function, you have to keep that limit notation the whole entire time. I know it's kind of annoying to keep rewriting it, but you have to. So until I substitute in x equals negative 3, I have to keep writing limit. So I am not substituting yet because I'm getting 0 over 0. So I'm going to keep rewriting this limit notation. So what I'm going to do is I'm going to try to get rid of this denominator by factoring the numerator, and hopefully something cancels out. Okay, so factor the numerator. I get x plus 3, x minus 2 over x plus 3. And you can see that these factors will cancel. So that means limit as x goes to negative 3 of x minus 2 is really the limit I'm looking for. And now I can actually substitute in because x plus minus 2 is continuous everywhere. So negative 3 minus 2 is negative 5. So that means the limit is actually negative 5. Now, if you actually graph this on the graphing calculator, you'll see that this graph looks something like this. So that when we are going to negative 3 from both sides, y is going to negative 5. So there's a hole. So when you get a 0 over 0, I would say maybe 80% of the time you'll see a hole. All right, so let's have you guys practice just these two. So this one's pretty much the same. This one, you gotta remember how to factor the difference of cubes. And this part is a little bit tricky, so try to think about how to factor that. Oh, I'm sorry, actually this should be x squared. X squared, there. Okay, so let's look at number 1. Very easy, the answer is 5 over 8. Just factor and then simplify. Number 2, if you don't remember how to factor difference of cubes, you use the slope method. So same, opposite, so plus there, always positive. So if you don't remember, a cubed minus b cubed becomes a minus b times a squared plus ab plus b squared. Okay, in the denominator, this is x minus 6, x minus 1. And so this cancels. We are left with limit as x goes to 1 of x squared plus x plus 1 over x minus 6. And then we plug in 1. 1 squared plus 1 over 1 minus 6. This ends up being negative 3 over 5. Okay, one thing before we keep going, if you plug in a number and then you get this, if you do write a equal sign, you have to write indeterminate form. We can never have a limit equal to 0 over 0 because 0 over 0 doesn't make any sense. It's not an actual limit, right? Limit has to be an actual number. This is not a number. So then what we have to do is I will kind of help you later on. But just remember, this is a big no-no in AP Calculus test. If you write equals to, if you ever write equals to 0 over 0, it's automatically you just pretty much lost the point for the entire question. So please do not write that. If you do, you have to write indeterminate form. All right. Let's look at number 4 really quickly. Just kind of refresh your calculus, algebra skills. So if we plug in 3 right now, we're going to get 1 over 3 minus 1 over 3 over 3 minus 3. We know this is 0 over 0, which is indeterminate form. So this is not okay, and the question is, how do I fix that? Well, let's try to fix it by combining everything into one big equation. So I'm going to rewrite this first. If you kind of recall from Algebra 2, we have two fractions, and this is kind of a fraction on its own. So we have 3 fractions. In order to cancel all the fractions at the same time, you need to multiply by the least common denominator. So if you kind of think of this as a fraction, we have 3 denominators. That is x, 3, and 1. So the least common denominator between all 3 is 3x. So if you do that, you will be able to cancel all of the denominator at the same time. So 3x times 1 over x is 3. 3x times 1 over 3 is x. And in the denominator, we have 3x times x minus 3. A little trick, again, the denominator is usually used to we want to cancel out some factors. So please do not distribute. Do not distribute this. If you do, you're going to have to undistribute or factor, and it's just a waste of time. So leave it in the factored form. Okay, 3 minus x and x minus 3 are pretty much exactly the same with the difference of a negative. So what we can do is take out a negative from that so that we can cancel that. So limit as x goes to 3 of negative 1 over 3x. Now it's safe to plug in negative 1 over 3 times 3 is negative 1 over 6. So the limit is negative 1 over 6. Second example. All right, find the limit. So limit as x goes to 0, again, plug it in. Square root of 0 plus 1 minus 1 over 0, we get 0 over 0. Indeterminate form. Please, again, remember to write this if you're going to write equals 0 over 0. So we cannot really do the same thing as before where we just kind of factor and cancel. So we have to try something different. And again, this is a technique that we learned in Algebra 2, which is we need to multiply by the conjugate, if you remember what conjugate means. Conjugate means you need to find the opposite sign so that you end up with a minus b times a plus b. So this is going to be x square root x plus 1 plus 1, and then do that to the top and bottom. So limit as x goes to 0. In the numerator, if you recall, this is a minus b times a plus b, which ends up being a squared minus b squared. So if you kind of think of this as this is a, this is b, this is a, this is b, we're going to end up with a squared minus b squared. So that is square root of x plus 1 squared. So x plus 1. And then b squared is 1, but remember there was a minus in between. In the denominator, remember I said do not distribute, because we know some things might cancel later. All right, 1 minus 1 cancels. We have an x in the numerator and an x in the denominator. That's very nice. That cancels. So then we're going to end up with this limit as x goes to 0 of 1 over square root of, I'm sorry, why did I put this really long bar here? Okay, so then this is equal to 1 over square root of x plus 1 and then plus 1. So then if we put in 0, we get 1 over square root of 0 plus 1, which is 1 over 2. So the limit is 1 over 2. All right, this is the rationalizing technique. So let's have you try one on your own. So go ahead and try number 1. Okay, the answer is 1 over 6. So we're in this unit of limits, and we're going to need limits for the future reference. So every time I teach you kind of a little things and I say, please be careful of this, please make sure you do this, do pay attention, because if you miss it on your test or quiz or anything like that, I will take a lot of points off. So first thing we talked about is keep limit notation until you substitute x. Okay, that needs to stay there. No equals 0 over 0 unless you write indeterminate form. Okay, so far we probably have only covered these two, and then I'll add more of these as we go on.